Two charged spheres in equilibrium. Two tiny spheres, so these are points, of mass 6.8 milligrams carry charges of equal magnitude 72 nanocoulombs, but opposite sign. Opposite sign. All right. They are tied to the same ceiling hook by light strings. Light strings, so we neglect the weight, and these are tiny spheres. Length L. When a horizontal uniform electric field E directed to the left is turned on, the spheres hang at rest, so we have equilibrium, with the angle theta between the strings equal to 58 degrees. That's angle theta here. Which pole, the one on the right or the one on the left, has positive charge? The one on the right or on the left? And what is the magnitude E of the electric field? Okay, so looking at this setup here, we have a distance d between these two spheres. Now, since there is a uniform electric field, this must point from a positive charge distribution toward a negative charge distribution. Because this is deflected to the right, this implies that the one on the right has negative charge, the one on the left has positive charge because it's deflected to the left. Alright, so electric field always points from a net positive charge distribution to a negative charge distribution. So a uniform electric field points from a net positive charge distribution towards a negative charge distribution, and therefore the sphere on the left must have positive charge because it's deflected to the left. Must have positive charge to be deflected in the minus I hat direction. You see that this is my x-axis pointing to the right. Now, what is the magnitude of the electric field? Let's look at the free body diagram of the right sphere here. The right sphere feels the tension of the cord, the weight mg, the force due to this external electric field QE, which is to the right, and then it also feels a force due to attraction from this positive charge to the left. So there's the electrical force due to the uniform electric field, the tension in the cord, mg, and the attractive force due to the other tiny sphere. And this is my x-axis, this is my y-axis. All right. Now, at the same time, I can read from this right triangle that sine of theta over 2 is d over 2l. All right. So let me note that here. Sine of theta over 2 is d divided by 2l, and d is equal to 2l sine theta over 2. And the net force on the y-axis, sum of the forces on the y-axis, is t cosine theta over 2, pointing in plus j hat direction, minus the weight mg. This is equal to 0. So I find that the tension is mg divided by cosine of theta over 2. The net force on the x-axis is the electrical force, F electrical, minus t sine theta over 2 in minus I hat direction. So this is t sine theta over 2, minus the attractive force. This must be equal to 0 because we have equilibrium. All right, so t cosine theta over 2 balances mg, t sine theta over 2 plus the attractive force balanced by the electrical force. Now, we can write these equations So we can say the electrical force is Q times the electric field E. And then we have minus T sine theta over 2. Now if this angle for mg, so we're going to have minus T sine theta over 2, so minus T times D over 2L for the x equation. But from the y equation, we have mg over cosine theta over 2. So mg over cosine theta over 2 substituted for t, sine over cosine will become tangent. So we have minus mg tangent theta over 2. That is basically nothing but the tangent times sine theta over 2. Tangent times sine theta over 2 is mg tangent theta over 2. And then we have the attractive force between them, minus 1 over 4 pi epsilon 0 Coulomb's constant, q squared over d squared. This must be equal to 0. So we can read electric field here as mg divided by q tangent theta over 2 plus 1 over 4 pi epsilon 0 if you divide this q squared with q here, we have only one q remaining on top. So this is going to be q divided by d squared, but d is equal to 2l sine theta over 2. So it's going to be 4l squared sine squared theta over 2. So finally, we see that the electric field is mg divided by q tangent theta over 2 plus, there are two 4's here, so this gives us a 16, 1 over 16 pi epsilon 0 L squared, and then we have q divided by sine squared theta over 2. That's the magnitude of the electric field. Now we can see that m, the mass of one sphere, was 6.8 milligrams, which is 6.80 10 to minus 6 kilograms. The gravitational constant g is gravitational acceleration g is 9.8 meters per second square. The charge on each sphere is 72 nanocoulombs, which is 72 times 10 to minus 9 coulombs. The angle theta divided by 2 is 58 divided by 2, which is 29 degrees, and the length of the cord was given as 0.530 meters. So that was L given here. Okay, so substituting the numbers, we can find the magnitude of the electric field. mg, it is 6.8 10 to minus 6 multiplied by 9.8 meters per second square divided by charge 72 10 to minus 9 coulombs. Tangent of 29 degrees plus 1 over 4 pi epsilon 0 is Coulomb's constant, 9 times 10 to 9, divided by 4L square, 0.53 square, Then we have the charge 72 nanocoulombs, 72 times 10 to minus 9 divided by sine square 29 degrees. And this calculation gives us electric field magnitude of 2.97 times 10 to 3 newtons per coulombs. Okay, so in this problem we have considered an equilibrium condition between two tiny spheres that are oppositely charged under the influence of a uniform electric field. From the direction of the electric field, we know that there is a net positive charge distribution at the origin and negative charge distribution at the tip of the electric field. Because the sphere is deflected to the right, it's attracted to the right, this has to be negatively charged, this has to be positively charged because it's deflected to the left. So that was part A. Part B is about the magnitude of the electric field. Provided that we have equilibrium established here, the forces are tension, the electrical force due to this electric field, the attractive force between the positive and negative charges, and the weight mg. So net force on the x-axis is 0. T sine theta over 2 plus attractive force balances electrical force, and T cosine theta over 2 balances mg. And this attractive force is basically k times q square over d square, where d is the distance between the two spheres at equilibrium. Now, for tension, we can substitute mg over cosine theta over 2, and t sine theta over 2 is mg tangent theta over 2. That's what we have here. For the electrical force, it's the charge multiplied by the electric field pointing in plus I hat direction, QE. And this is equal to 0. From this equation, we can obtain the electric field magnitude. Now we can substitute the numbers given and convert to SI units, and this gives us our final answer.